the solutions to question number 4 for the 2015 summer examination paper for linear algebra and programming skills. So for part A, we want to, we're considering this linear transformation here, t from polynomials of degree 2 into three-dimensional vectors. So for part A, we want to determine t of this polynomial, and for part 2, we want to determine a non-zero vector, p of x, which is it's a polynomial of degree 2, such that t of p of x is 0. For part B, we want to prove that this mapping, t from p2r to v3r, is indeed a linear transformation. So for part A, for A part 1, we want to determine t of this polynomial. So you can see here that a0 is 1, a1 is 1, and a2 is minus 1. So if we substitute those values into this right-hand side for a0, a1, and a2, then we get this three-dimensional vector. For part 2, we want to determine a non-zero vector, which is in p2r, such that t of p of x is 0. So if we take t of a0 plus a1x plus a2x squared, we know we get this three-dimensional vector. But we want this three-dimensional vector to be 0, which means that each component has to be 0, which means that a0 plus a2 has to be 0, so a0 is minus a2, and a1 plus a0 has to be 0, so a1 is minus a0. So therefore, if we put a1 is minus a0, and a2 is minus a0, and a0 is 1, then you can see that p of x is 1 minus x squared. This vector here is in the kernel. Okay, so t of this polynomial does give you 0. So this polynomial is in the kernel. So this polynomial is non-zero, so we found a non-zero vector such that t of p does give you 0. And of course you should all know that t of 0 is also 0. Okay, but this is another vector which gives you 0. Okay, so for part B, we want to now prove that this mapping, so t from this polynomial space into three-dimensional vectors, we want to show that this mapping is a linear transformation. So we need to prove that t of alpha u plus v is equal to alpha t of u plus t of v. So this is what we need to prove. So this is what we need to show to prove that t is a linear transformation. So we take two general vectors, which are in P2R. So u is the first vector, a0 plus a1x plus a2x squared, and v is another general vector, b0 plus b1x plus b2x squared, and both of these are polynomials of degree at most 2. So that means the highest power is 2. And we take alpha as a real number. So t of alpha u plus v is the same as t of, so we have alpha times u is this polynomial, plus v is another polynomial. So within this bracket, we can now perform scalar multiplication and addition of polynomials, which you should all be able to do. So t of alpha u plus v is t of. So now we want to know what is the new constant coefficient here. So the new constant coefficient is alpha a0 plus b0. That's the new constant. The new coefficient of x is alpha a1 plus b1. So from alpha times this plus this. So there's the new coefficient of x. And finally, the new coefficient of x squared is alpha a2 plus b2. So that gives us the new coefficient of x squared. We now apply the mapping t onto this polynomial. So here's the mapping. T of the polynomial gives us this three-dimensional vector. So we apply this mapping to this polynomial, and here is our resulting vector. And you can see that the first term of this vector, we take the constant coefficient and we add the coefficient of x squared. So here we've taken the constant coefficient and we add the coefficient of x squared. So this is the constant coefficient plus the coefficient of x squared. You'll notice that the middle term of this vector is always 0. So we put a 0 in there. And then the third term, we have a1 plus a0. So we have the coefficient of x plus the constant coefficient. And now here is a trick we use in maths. We can either write down the answer, because we know we're trying to prove that t of alpha u plus v is alpha t of u plus v. And at this stage, we could work backwards. So you'll see that alpha t of u is alpha. So here is t of u, which was up here, t of u. So this is alpha t of u. And here, this expression is t of v. And you should be able to see that you can split this vector into these two vectors. So this is true. So therefore, we've proven that t of alpha u plus v is equal to alpha t of u plus t of v for general vectors u and v in P2R. So that concludes the solutions to question number 4.